Okay, hello everyone and welcome back to C Mathematics. We're going to be continuing on with some encryption stuff, and today we're going to be looking at the secure hash algorithm. So just a pre-note, this has nothing to do with the actual topic, but it has been however long since I've last done anything. Basic reason is it's been a hectic month, but I've moved back into school, so I now will have more of a regimented schedule, and from that I can then develop I can integrate streaming and doing YouTube back into this schedule, so I can upload more regularly. But I have worked on a bit of code in my off time, including the secure hash algorithm. So, I'll probably end up doing an update video at some point just to explain a few things, but this music keeps cutting out, which is no bueno. I'm just going to get this online. It's going to be distracting if this keeps cutting in and out. But today we're going to be looking at, we're going to start by explaining hash algorithms in general, and then we will look at how you can apply them for encryption and other places, and then we will look at how the SHA algorithm works, or also known as Keccak, I think it is. Yeah, that's it. And how that function works, all the parameters, all that stuff, and then we'll be writing the code in C to integrate with our other encryption stuff, which is pretty cool. Alright, so let's hop into OneNote. Okay. This is working. Good stuff. Okay. So, hash algorithms in general, or hash functions, is essentially a mapping function. So you map any data value, so some data value x, data x, and it goes to y via the hash function h of x, where y is in a finite set. So there can only be so many values of y. So we can put this in, I'll call this the set h. So for example, what could this finite set be? When we've looked at hash tables before, essentially what hash tables are is you take a data value and then you get its index based on its value. So if we had an array, so for hash tables, and we have our array here, so let's say we have 6 slots, so n is equal to 6, so 0, 1, 2, 3, 4, 5. Now a common hash algorithm for a hash table is you just take a data value, say we're storing integers, and we just take h of x is equal to x modulo n, or x mod n. So for example, if we wanted to insert the value x is equal to 6, or x is equal to 2, then h of x is equal to 2. So we put the value of 2 at 2. And if we want to do x is equal to 7, h of x is equal to 7. Or h of x is equal to 1, sorry. And then we store the value 7 at index 1. So that's how hash tables kind of work. In cryptography, it's going to be kind of similar, specifically with the secure hash algorithm, where we want to securely hash a value to a finite data set. But this secure algorithm is only secure when the function is one way. So where h of x cannot be reversed. So h inverse of x is hard to find. So it's kind of like RSA encryption, where the opposite is cannot be obtained so easily. So with encryption, what this does is, if we can securely take a value, like a password, so let's say we had our password P, and we take the hash of P, this gives us some hash value, and because H is hard to reverse, we can't determine what P is from that password. So going to P is not viable unless you're doing brute force. With this x mod n, it wouldn't be as difficult to find the inverse, but there are ways to make this more secure, or there's stuff like that. But the secureness in a hash table is not as, we're not as worried for a hash table. This is more for encryption. So if we take the hash of a password, we can then store this hash in a database. So we'll have a database, and we're going to say let's store h1, which is equal to h of p1. So we're storing the hash of password 1. So when a user now logs in, so the user sends p1, or the hash of p1 over, because you're not going to send the actual password over the internet. So you send h1 over, and you compare it in the database, and if you get the correct hash, or if you compare the hashes, so h1, h2, h3, etc., and then we send back an OK. Now the beauty of this is, if either the database or the internet connection is insecure, the password is still protected because it's stored in a hash. So if a hacker is able to see in the database, it only sees hash values, which once again, you cannot get the original value of a hash without using brute force or some other complex technique, but it still takes a long fucking time. Because with the hash, in the SHA algorithm, so the secure hash algorithm, which is used for cryptography, we're going to be hashing any length value, so values of any length, so strings with any amount of characters to some security level, and that security level is a parameter. So let's say you had SHA3 256. That would map it to 256 bits, and that's going to be, is that 64? I forget how many bytes that is. 256 divided by 8 is, why can I not remember this? I'm blanking on this one. 32. So 256 has 32 characters. So the hash value in SHA-3 to 256 has 32 characters, so the result. So you pass in any string of any length, and it will compress it or extend it. It will just put it into a string of length 32, no matter what the length is. So once again, the purpose of this hash is if we store the password in the database using a hash, if someone taps into the internet connection or gets access to the database, they only see the hash, which is non-reproducible unless you use a brute force technique. Okay. So yeah, that's pretty much how that works. Now there's one extra note on hash functions, and that's collisions. So you may have noticed, well, if you're putting it into a finite set, what if two values map to the same output? That's easy to see with the hash table. If we had x is equal to 14, then we have h of x is equal to 2 as well. So what do you do here? You can't just put the 14 in there. Well, some algorithms will put the 14 over here, or some algorithms will chain the 14 to this slot right here, using a linked list or something like that. With cryptography, it's the same thing. So the goal is to minimize collisions with your hash algorithm. That's the goal of any hash algorithm. So for the hash table, you don't want to be putting values at the same index, because that would just make things harder. So you're going to so if a hash algorithm is more efficient, then it will organize the values in a better way, so there's less collisions. And then with the encryption, if you have fewer values, if you have a better hash algorithm, it will make it so that fewer values can map to the same output. So if we have a higher security level, so for 256 bits, there's 2 to the 256 possible combinations. So you would need to brute force that many fucking things to get a hash that works, or to match the hash. But if you have 512, you have 2 to the 512 possible combinations, which is much more difficult. So that's how collisions work. Alright, so let's look at the Keccak function. I believe it's pronounced Keccak. One second. Fire truck going outside. So let's look at Keccak. This is essentially just another name for SHA3. Well, essentially Keccak is the function, and then we just have I am not entirely sure about like HTTPS protocol, but I was just realizing that, like, can't you just send the hash over? But I think the purpose is you can I think the user will make the hash and send that over the internet. But the thing is, I believe it's not easy just to send. It's not as simple as sending the hash over. You have to enter the password through the user's form, or the online form, and that will generate the format that you need. So it may. I'm not entirely sure how that works, but the thing is, the point is, the database stores the hash values, so that even if a hacker does gain access to a database, then it will it won't have access to passwords. So it will only have access to hash values. No problem. Okay, so let's look at Keccak right now. So essentially, we go through a bit of pre-processing, which is just padding, and then we go through two phases of the actual function itself to get our hash value h of m, where m is just a message. So for absorbing, there's just two phases: absorbing and then squeezing. So absorbing is when we take in multiple blocks. So each one of these x values is a block, and depending on the security level, you will have different size blocks. Well, the blocks will all be the same, but the number of blocks will differ based on the security level. So we essentially take our message, divide it up into blocks, pad those blocks if needed. So we have x0, x1, ... x t minus 1. And then to the output, we will continue getting blocks from the output until we are able to fill the sufficient size. So for 256, we need to fill 32 characters, and we will be taking this number R blocks every time. So let me explain what a few of these parameters are right now. So the first one we want to know is that there are two values, B and L. So L determines B. So for SHA3 we have, or let me just put some values here, and then they're predetermined values for SHA3. So L is just our first parameter, and the predetermined value by SHA3, the standard value, is going to be 6. Then B is going to be equal to 25 times 2 to the L. So for SHA3, B is equal to 25 times 2 to the 6, which is equal to 1600. Now B is equal to R plus C. Now these two parameters are determined independent, or they're not determined independently. R is determined by the security level in SHA3. So we have SHA3, 128, 256, 512 are just the three main ones, and then you have other ones as well. We're only going to be looking at these three right here, but it would be easy to integrate the other ones. So for a level of 128, R is equal to 1344. So therefore, we have, so R is determined by the algorithm, and then C is equal to B minus R, just by algebra. So if R is equal to 1344, then we have C is equal to, what's 1600 minus 1344? I don't know. It's some value. Doesn't make a difference. And then for 256, R is equal to 1088. And then for 512, we have that R is equal to 576. So what are these two values, R and C, and B for that matter? B is essentially the total block size that we will be passing into the function. So you see that each block here that we pass into the function is R plus C, or a block of size B. Now R is what we call the bit rate. And the bit rate is essentially the rate of bits at which we absorb and send out bits. So you see in the absorbing phase, we're taking in blocks of the message R bits at a time. So for security level of 128, we'll take in 1344 bits at one time, and then you see that number decreases as the security level increases. And what that means is C, which is the size of this second block, which is going to start as all zeros, so these are going to be all zeros, this is just going to be that kind of extra, I don't want to call it padding block because the padding is something different, but it's just the extra block where we can just to add for more security and more to give more space for operations, so that we're just not operating on the message and we have some extra data that can help change the hash or modify the hash so it's less similar to the, or not less similar, but so it's more secure. And if you have more space, then we have less of the message coming in at a time, so we run the function more times, which also makes it more secure. Now, each time we run the function, you see that we call the function many different times for each phase, or for each round of the phase. Each function has multiple rounds of itself, and this is determined by NR, and NR is also determined by the parameter L. And NR is equal to 12 plus 2L. It's going to equal to 24. So in SHA3, we have 24 rounds of Keccak per call to Keccak, or 24 rounds of these of this sequence here per call to Keccak. And this is essentially just one round where we go through theta, rho, pi, chi, and then iota. Those are the 5 functions or 5 operations that we will do on each round. So once again, just as a recap, we have 2 big parameters, or 2 needed parameters into the Keccak function. So Keccak needs a value of L and a value of R, and then the message whatnot. And SHA3 takes in a value of R and M, and will call Keccak how many ever times using the value of L as 6, the value of R, which is based on the security level, and then the message. Where once again, R is determined by these 3 things over here. Like that. Okay. So yeah, that's just to make this a little more clear. We have that each call just gives us this 24 rounds. So each call to Keccak, we will then call, or we will do these operations 24 times. All right. I'll leave that open actually. So let's look at, next thing we're going to look at is the state representation actually. Because we have blocks of R and C, but the way we're going to represent these is going to be very important. So our state we're going to represent using, it's going to be called A. So that's just, this is from the official NIST document that I linked below. So each state we're going to represent as a 3D array, where we have 25 values in each slice. So you might be wondering, well, where does the 25 come from? Well, that's just from this calculation of B right here, like that. And then the width of this rectangle is going to be W, which is going to be 2 to the L. And in this 3D box, each one of these cells are going to be individual bits, not bytes, individual bits. So we have a 0, I'm just going to put random values in here. Like so. So it's individual bits. Make sure that's just one thing that has to be clear. It's individual bits. So for SHA3, we have 2 to the 6, or 64 bits in each what's called lane over here. This is the lane. So that's also going to be called the word size for SHA3. And 64 bits, you might be thinking, well, what are we going to use? Well, it's going to eventually be a long, or a long. Oh, no, that's just my charger. So we have 64, or we're going to have 25 longs, longs, or 25 words of 64 bits each. And we're essentially going to read in values. Let me just make sure I forget exactly how you do it. So we're going to be reading in values by each plane. So we'll start at the bottom plane. So we go insert values in 0, 0. So over here, then we go 1, 0. So we go by x. So we iterate across x first. Then we go to the next plane, which is y equals 1. And that's essentially how we're funneling in our values. Now, once we get to our bits each round, or each, once we get our bits, then we're just going to leave the rest as zeros. So, for example, with a security level of 200 or 512. Oops, no, don't do that. 512. Once we get to 576 bits, which is going to be 72 bytes. So once we get 72 bytes, which is about 72 over, there's 8 bytes per, that's 9 words essentially. So we have, I can also just do 576 divided by 64, and we get, or no, 576 divided by 64, we get 9 words per block. So every time we're reading in a block, we read in 9 different words. So we do 1, I'll erase some of this stuff here. So we start by funneling in 64 bits here. (64 bits), 64, 64, 64, and then we go to the second row, or the second plane, 64, 64, 64, and then 64, and that's 9 words. And then the rest are just going to be zeros. Yeah, and all of these are going to be zeros too. I'll just draw it in so you guys can see. Or, yeah, it doesn't matter. But yeah, so everything after we've read in each block will just be leftover zeros. Alright, so now let's look at a few of these steps in general. So we have the high level view. So we do our pre-processing, which involves padding. Then we're going to do a bunch of absorbing steps and squeezing steps. And all that's left is, so we know that we need to read in we're going to essentially XOR in each block from the message every time. But now, what does this function include? Well, we know it includes 24 rounds of this process here, which is going to be theta, rho, pi, chi, and then iota. But what are these operations? So for theta, theta is considered just an XOR with neighbors. So this is a graphical representation of it, where you take the bit which is in the dark gray, and then we're going to XOR it. It uses a summation notation, but in binary, summation is just another word for XOR. So we're going to XOR the neighboring bits to the column directly to the left. So x minus 1, same y, same z, and then to the in front of and to the right, so it's going to be z minus 1 and x plus 1. So just the XOR of the 11 bits there. For pi and for rho and pi, essentially we're going to, it's an XOR and then a rotation. So we do rho first. So we essentially just create an auxiliary array with rho, I believe. Where is it? Theta. Yes, with rho and pi, we're going to create an auxiliary array where we kind of rotate values in rho, and then for pi, we take the columns and then just like shift them around. So that's shuffling. How long has it taken? It's been a while. I think I started it last September, so about a year ago. But I haven't been like extremely focused on it. I've just been adding. I've done a bunch of this stuff, but yeah, I'm doing some more encryption now. But yeah, so it's been about a year or so. So we have the pi, which is just a shuffling of all the columns from the auxiliary array, which was, once again, the shuffling and the rotations. Okay. Now for chi, this is essentially just a manipulation where we're going to, it's an XOR and then an AND, or an AND and an XOR, where we shuffle some more, or shift each row, or is it each row? I forget exactly what it is, but yeah, I guess it is a single row. So chi affects single rows, and it's essentially an XOR and then we just shift them over. And then for iota, we simply just take values and XOR them with the round coefficient, which you can compute, but we will also just have a table because we only have 24 rounds, and the round coefficients you can calculate for any t, but we're just gonna keep the table just for simplification. Okay, so yeah, those are the steps. So every time we call Keccak f, every time we call Keccak f, we're going to go through 24 rounds of theta, rho, pi, chi, and then iota. In that, well, the order, I'm not going to go into too much detail here, but essentially theta is the only thing that has to go first. All the other steps, you can kind of move them around and it won't make a difference. I think that's what it said, but might be wrong. Don't quote me on that. But yeah. Oh. This is weird, but okay. So yeah. Alright, so now we have somewhat of a foundation, but I mean, those fine level details are not really important until we actually go to write the code, but essentially make sure you understand just how the high level stuff works. Once again, we're just going through rounds. We have a bunch of absorbing rounds and a bunch of squeezing rounds, and then in each round, we're going to call Keccak, which has 24 rounds of this procession right here. Alright, let's write some code now. So I'm going to create 2 new files. I'll call it SHA3.h and SHA3.c. Alright, so for the header file, we will start with our macros. So we first just have to include cmathematics.h. Then we're going to do our if not defined. So if not defined, SHA3h, define SHA3h, and diff. Alright, and then we're going to have macros for the parameters here. So we're going to start by defining L, or SHA3L, as 6. That's just the base parameter. Then we have define SHA3NR. And I'm going to try and do something. 12 plus 2 times SHA3L. Does that work? Yes, it does. Okay. So NR is going to be this value here. Then we're going to define SHA3B as 25 25 times 2 to the L, which is just going to be 25 left shifted by 6, or by SHA3L. Does that work? Alright, let me just make sure this actually works. Test AES, yeah. Alright, so I can delete the main test here. Alright, so CD test, debug, and I'm going to break 23. Run. Let's print SHA3L. No, doesn't work. We have NR. So I'm just going to print out these values just to make sure that, okay, so yeah, 624, 1600. Good stuff. So yeah, that's just how those values are determined from L. Next, we're going to take care of a few utility things, and then we will actually start writing the hash function. So we will do we'll have our reference tables. So extern, unsigned integer, SHA3 rotation constants. That's going to be a 5 by 5. So essentially, when we call the function, when we call row and pi, I think it is it a row? Yes. So for row, there's another table that we will need to use to take the offsets of row. So, where is the? Yeah, it's just another. It's a 2D array, and each lane has its own corresponding amount that it needs to be shifted by or rotated by. So, for example, you see the value at 0, 0. So the lane at coordinate 0, 0 needs to be rotated 0 places. Now at y is equal to, or at 3, 0, so the third lane in the bottom plane needs to be rotated 28 bits, and essentially we're going to rotate it towards z equals 0. So it will come, where's the block? It will go so the rotation goes this way. So we rotate it 0 places that way, and then you rotate it to the back as well. Alright, so that's why we're going to need this rotation constant table, and that's why it's a 2D array, because we need one value for each lane. And then we have an extern, unsigned, long, SHA3 round constants. And that's going to have a size of SHA3NR. So once again, we have one round constant per round. So we need 24 of them. So I'm going to go ahead and paste this into SHA3.c. Well, I first have to include SHA3.h, and then I'm going to paste these two table, or actually no, we don't need to paste them because there is a paste bin that I created, and it has these two things over here. Link is down below somewhere. Why does it not? Yeah, there we go. So yeah, these are the predetermined values for the rotation constants, and then also the round constants. All right, so those are our reference tables, and we're going to use them a few times when we actually write the function. All right, now we're going to need one more utility method, and then we can write the actual hash function. So we're going to have an unsigned long return, and once again, for each lane, we're going to be using an unsigned long. I mean, we could probably do a long, but I don't know exactly how bitwise shifting is going to work if we used a signed long, so I'm just going to keep it as unsigned for now. So an unsigned long, return type, SHA3 rotate word. It's going to take in an unsigned long W and an unsigned int D for the number of places to shift. So we take in a lane, W, or a word rather, and shift it D bits towards the front. So I'm going to copy this signature over, and I'm going to walk through how we're going to do this. So since we have to shift the bits, we're gonna want to kind of just divide it up. So I'll just write this down for illustration's sake. So if we are shifting this lane, let's say this is our lane W, and let's just say that there's 64 bits here. So D is equal to, so W is equal to 64, and D is equal to, let's say, 3. So we want to rotate it 3 bits this way, and then put those 3 bits on the end. All we're going to do is we're going to take the 3 bits up front, chop them off, or copy them into another value, and then just paste it on the end there. So what we're going to have to do is, let's say that we had a 1, 1, 1, and a bunch of zeros. What we're going to do is we're going to take a mask. So our mask is going to be, just going to be, let's say this was actually 1, 0, 1. So to get these 3 bits, we need a mask. So we'll have our mask 1 is equal to 1, 1, 1, and then zeros. If you don't know how mask works, essentially if we want to just take a few bits of, or some specific bits, we're going to just activate the bits that we want in the mask, because when we bitwise and the mask with the value, anything bitwise anded with 1 is just the original value, so it will take the values. So when we do mask, so W and mask 1 is equal to, let's just put another 1 in there just for illustration's sake. This is going to give us 101, and then the rest are zeros. Because, so we have the initial 3 values here, and those are bitwise anded. So we get a 1, 1 and a 1 is a 1, 0 and a 1 is a 0, 1 and a 1 is a 1, and then for the rest of these values we have something bitwise anded with 0, which will always give 0. So now that we have the 3 values, we want to essentially right shift this by, so I'll call this end, is equal to that, and then we want to essentially get these, or let's do the start too. is equal to W and mask 2. And you can just assume that mask 2 has all the other bits activated. So it's just the 1, 1, 1. It's like that. So mask 2. So W and mask 2 will just give us a 0, 0, 0, 0, 0, 1, and then the rest zeros. And then now we want to put these together where the end is on the end. So we're going to take end right shifted by, I believe it's 64 minus D, or left shifted, because this is going to be the least significant bit. Or wait, oh, hold on, hold the phone. Oh, I screwed this up. If you're considering this as, I didn't, if you're considering this as the least significant bit. And this is the most significant bit. Let's do that for now. Just, so we're going to do end is going to be shifted to the right. So towards the most significant bit, and whether that's right shift or left shift, it's up to you. But it's going to be left shift, I think, in C, because left shifting is just multiplying, is moving towards the most significant bit. So we left, right, or shift towards the most significant bit, 64 minus D positions to get a 0, 0, 0, 0, 0, 0, dot, 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 101, and then start is going to be, we're going to left shift it by D, or shift towards the least significant bit by D, which will give us a 001, and then when we add the 2, we'll get a 001, which is the rotated version. I know this is probably seems very complicated, but essentially we're just using masks to copy and paste bits in different places. So what we're going to do is we're first going to bitwise or modulo D with 64, so that we only want to rotate it 64 bits, because otherwise we're going to be shifting by some value way beyond which we do not want. So we first have to reduce D so that it's within 64. So we're going to say D is equal to D bitwise and with 0x3f, which is the equivalent of D mod 64, because 64 is the power of 2. So to get the modulo, we just need to chop off the rest of the bits. All right, then we're going to use our mask to get, well, to actually get the mask. We're going to first need the unsigned long maximum value, which is the opposite of 0L. So we're going to take the complement of 0, which just gives us all 1s, and then we're going to use this max to get our masks. So we're going to say unsigned long wrap portion is equal to max left shift, so in parentheses max left shifted by, then we're going to do 64 minus D bitwise anded with W. So once again, we take the mask 1, which is just going to be all 1s, and we're going to shift it towards the most significant bit by 64 minus D positions. So if D is equal to 3, then that's going to be a 61 shift towards the most significant bit, which is yeah. So this works. So we're essentially getting the leftmost, get the D most significant bits. Hold on. Yeah. and then unsigned long, shift portion, and then when we do the bitwise and that's just doing the mask operation. And then here we're going to do a max right shifted by D, that in parentheses bitwise ANDed with W, and this gets the D, or the 64 minus D least significant bits. Is this right? Hold on. Yes. Wait. If I want to do... Okay, yeah. So the way I was... When I was writing this code, I had to kind of play around with how memory is actually arranged in C. But the way it worked was we're going to be putting in... am I saying this right? We're going to want to align it so that the most significant bits are going to be the front of the array. So where Z is equal to 0. So the most significant bit in the word, in the unsigned long, is going to be the front of the array. So if we consider this lane as an unsigned long, we're going to have the most significant bit here at Z is equal to 0. And at Z is equal to 63, we have the least significant bit. So that's how we're going to be arranging this in C. And then we're going to shift these values to put them in place. So wrap portion, right shift equals by 64 minus D. And that's this over here. So the wrap portion is what we called end. So that's just going to be the stuff that we wrap around. So this stuff is end, and that's what we wrap around to the end. And then start left shift equals, or shift portion, left shift equals by D. And then we're going to return the addition. Should have zoomed in, I'm sorry. So we're going to return wrap portion, bitwise OR with shift portion. So in essence, all we've done here, I've taken way too long to explain this, but all we've done here is we're just copying and pasting bits in different spots using shift, or by shifting them. Okay, so that is our utility method, and now we can actually write the hash algorithm. So we're going to start by doing our two definitions. So we'll do the Keccak round first. So void, return type void, SHA3 Keccak round, and this takes in an unsigned long, what do I want to call this? I'll call this parameter A55. So it's a 5 by 5 2D array of an unsigned long. So I set a 3D box of bits, but each bit or each lane is a long. So you can just consider this as a 2D array of 64-bit words. So unsigned long A is 5 by 5, and then a character I, which is going to be the round number. And then a return type int, SHA3 hash, and this takes an unsigned character pointer in, so this is the actual hash function. This takes in the message, the integer n, the integer mode, so the mode will just be the security level, which we have to create macros for, and then the unsigned character double pointer out. So this is similar to how we did it with AES, where we're going to pass in the reference to a string so that we can allocate to that reference. And then for our macros for the security levels, we're going to do just define SHA3 128 as 128 define SHA3 256 as 256, and define SHA3 512 as 512. And then we will return the integer, which is the length of the hash. And once again, that's determined on based on the mode. All right, so let's copy these signatures over. And we'll start with the actual hash function first, and then we will write the Keccak function, the round function. Hold on. I think I need to fix my terminology on this stuff. Keccak is the whole thing. So I'm going to call it Keccak round, just one of these calls. So a Keccak round will just be a call to F. So I will actually change the second or the first function to SHA3 Keccak F. Where F has the 24 rounds. All right, so for our hash, we are first going to do a few things. So we are going to have to determine parameters based on the security level. So we're going to have an integer r and a ret length. So if we do a switch mode, we're just going to do cases on the modes. So case SHA3 128, we're going to say r is equal to 1344. This is in bits, and then break. Case SHA3 256, r is going to equal 1088, then break. These were once again determined, or these are just the values that I wrote up here. And those are also in the specification. And then case 3, which or just default now, which we're going to default to SHA3 512. We're first going to set the mode to SHA3 512. Then set r is equal to 576, and then break. And then after this switch, we're going to set the parameters. So we're going to say ret length is equal to mode right shifted by 3. So we're going to divide it by 8, convert it to bytes. And then r right shifted equals by 3, which is going to also convert it into bytes. All right, then we want to set our state variables, which is going to be the unsigned long A, which is going to be a 2D array of 5 by 5, and then we want to set this to 0. So mem set A, the value is going to be 0. Oh, I also forgot a bunch of includes. I'm sorry about that. So apart from SHA3.h, we need to include string.h, include standard lib.h, and then that's all you need. Or we could also just include standard.io just for good measure. But we're going to mem set A with the value of 0, and the number of bytes to set to 0 is going to be 5 times 5 times the size of an unsigned long. And this just sets consecutive values to 0. And the reason why they're consecutive is because it's a 2D array, and a 2D array of primitives or a 2D array is just going to be 25 consecutive values. But you can just access them differently. So this is going to be our state variable, actually. And then now for, sorry, we're going to have multiple. Then we need an integer cursor is equal to 0. So this will just be our cursor in the message. And then an integer number of blocks is equal to n divided by r plus 1. So the reason why I do a plus 1 is similar to AES, we're always going to pad, no matter what. Just because, so the way the padding scheme works is, if I want to, do I have it up on me? I may not have it, but give me 2 seconds. I think I can find it. Okay. So this is just a textbook chapter on this stuff. Here we go. So input padding. So essentially we take the message, and this is in bits, and we always pad at least 4 bits, which is going to be a 0, 1 after the message, then a bunch of zeros. Or sorry, it's a 0, 1, 1, then a bunch of zeros, and then a 1. And this is in bits. But because we're passing in a string, this is going to be 4 extra bits, and we can't just like, we're not going to get in, we're not going to be able to like insert it in, because each character or each character takes up 8 bytes or 8 bits. So we're not going to be able to kind of like, we're not going to get a length, a message length, which is not a multiple of 8 bits. So even if we do have a complete block at the end, we still need to pad 4 bits. And that will always end up, we're going to end up padding a multiple of 8 bits, just because we're going to be padding characters. So the point is we're always gonna pad. Now, we're also gonna have an integer I for the block counter. So we're gonna now do the absorbing phase. So we're gonna have a for empty first case. I is less than number of blocks. I plus plus. All right, now in each block, we're going to have a bunch of variables too, so block variables. So integer number of bytes in the block is going to be equal to the minimum. Now, I'm taking this minimum as the macro from cmathematics.h, which is, it's just these, so it's just a minimum and maximum function. So it's going to be the minimum of r and the maximum of n minus cursor and 0. So what does this stupid thing mean? So we want to take the first argument I'm going to talk about is the maximum. So maximum of n minus cursor and 0. So if the cursor is beyond the end of n, it's going to be a negative value. I don't believe this will ever happen, but just in case it does, I don't think this should happen. I don't want it to be a negative value, because then the minimum would give us a negative value, which we don't want. So otherwise, if the cursor is like not at the end of n, and we have more than a complete block left, I don't want to be on the assumption that we're going to be passing in the rest of the message in. So we want to take at maximum. So essentially, we just want to go only take in between 0 and r bytes. per block. That's just me saying that complicated sentence was just, I'm bounding our argument here. So n minus cursor, I want number of bytes in a block to be between 0 and r, but it can be this. So if n minus cursor is in between 0 and r, that's going to be the only time when it is not 0 or r. So when we don't have a complete block left. So as a result, we're going to say integer number padding is equal to r minus number of bytes in a block. So that's just the number of bytes that we need to pad. And then we're going to have an integer pad index, which is equal to 0. And an integer block cursor is also equal to 0. Alright, so before we do anything, we need to XOR the block into our state. So once again, our state is, in total, we have a state that is b bits long. So A is 5 by 5 by 64, and this extra 64 is just each unsigned long. Now where have we seen this? 5 by 5 is 25, by 64 is 1600. Oh, that's a B, and that's where we get our 25 times 2 to the 6. That's kind of the point. Well, the 25 was just based on the description of the algorithm, the reference tables and all that, the rotation constants. But then the 2 to the 6 was determined by SHA3. So that's going to be the length of each word. L determines the length of each word. And if we consider this B here to be our string of 1600 bits, we're going to pass each state, each block of, or each 2D array of unsigned longs into each function. Then we want to first XOR in our message into this block, into the state here. So we're going to XOR the block into the state. Oops, that's not what I want to do. Alright, so to XOR the block into the state, like I said before, we're going to be going in plane by plane. So we'll iterate through y on the outer loop. Integer y is equal to 0, y is less than 5, y plus plus. For integer x is equal to 0, x is less than 5, x plus plus. Alright, so we're going to have an unsigned long temporary value is equal to 0. And we're essentially going to XOR into this temporary value. And then, once we have done that, we're going to XOR into the, we're going to write into the temporary value, and then we're going to XOR the temporary value at the end. So, write into TMP, and then XOR the TMP into the state. So, to write into the temporary value, we're first going to need to determine what to write. So if the block cursor is less than r, meaning if we have not written the complete block yet. And if not, we need to determine what to write. So we're first going to determine how many bytes we want to write from the actual message. So integer number of bytes in the word is equal to the minimum of 8 and the maximum of number of bytes in block minus block cursor. So, and this is minimum with 0. So this is the same kind of thing that we did up here, and this time we're bounding between 0 and 8. 0 and 8 being number of bytes, which is just the size of a word. So we want to determine how many bytes from the message we're going to take, or how many bytes we're going to take from the message and put into the word. We could either take a complete word, 8 bytes, or we might not have enough in our block. So we might take like 6 bytes and then pad it with 2. So do that, and then if there are the number of bytes in Word, or in in Word, make sure that that value is in Word. Then we have stuff to copy from message. So write values, or write bytes from message. We're going to say mem copy. So we're just going to copy over memory. Destination is a reference to temporary. And we're going to, the source will be in plus cursor plus block cursor. So we go to the current block with cursor, and then block cursor goes into the current block. And then the number of bytes to copy over is number of bytes in Word. Yeah, I'm trying to think about how I can do this more efficiently, but I'm gonna have to switch around the x and the y in the index for our state. I'll look at that later, but for now I'll keep this as is. We're essentially just writing in lane by lane. Now, determine if we need padding in this word. So if the number of bytes in the word does not equal 8, then we need padding. So we're going to say if the not pad IDX, we have not started padding. So first padding byte, pad with the 0, 1, 1. So must pad just means with a 0, 1, then a 1 and a bunch of zeros and then a 1. So that comes from this. So in the first padding byte, once again, we're going to be padding with a 0 and 1, 1, which is just as 6. So we're going to say temporary, bitwise or equals with the unsigned long conversion of 0x06, and we need to convert this to a long so that we can shift it properly and still pertain the memory. And this is going to be left shifted equals by number of bytes in a word left shifted by 3. And we're going to be left shifting by 3 to convert from number of bytes to number of bits. So once again, this 0x06 is the actual padding that we need, and then we're going to be left shifting it to get the number of bits. And then otherwise, or not otherwise, we're going to, after this if statement, we're going to say if pad IDX is greater than or equal to number of padding minus 8, then we need to pad the last byte. So we're going to say temporary bitwise or equals a 0x0, ooh, how do I want to do this? I'll say you know what, let's do it this way. We're going to say an unsigned long the unsigned long version of 0x01, and we're going to left shift this by 0x3f, which is going to be just a 1 at the end. And 0x3f is just 64. Or 63, rather. Because we don't want to shift to 64 because that would just throw it off the word. But we want to put it at the end. And the reason why I didn't do an else if is because the first padding byte could also be the last one. Like let's say we had a complete block except for 1 byte, then that last byte that we have not filled yet will be both the first and the last padding byte. And these would both be in the same one. And then otherwise we're going to leave as zeros. And then after this we want to increment the padding index. So pad idx plus equals 8 minus the number of bytes in the word. Alright, then after we write into the temporary value, we're going to XOR the temporary value. So A at X at Y, XOR equals with TMP. And then we want to advance the block cursor. So block cursor plus equals 8. And then after after the double for loop here, so after the X and Y, make sure you know which one that is, we're going to advance the message cursor. So cursor plus equals number of bytes in the block, which is just how many of our bytes we add in the block to advance by. So once we have read them, we just want to go to the next block. All right, now we call Keccak f, which is just going to be so we call SHA3 Keccak f, passing in our state, which is going to be A, and the index will be I. Oh wait, no. Sorry, we need to update Keccak f. Keccak f only takes in this state the 2D array, not the index. That's going to be dealt with in the actual function f. I wrote this differently, but I'm realizing this terminology is more clear. All right, so this is Keccak f, and then now we're going to, now that we have absorbed everything, we're going to do our squeezing round, or squeezing phase. All right, actually above here, I want to allocate the output, or do I want to do that later? You know, let's allocate the output above everything. So we're going to say dereference out is equal to malloc ret length times the size of an unsigned character. So we're just allocating memory, and we're going to point, or it's essentially we're just allocating memory for a string at output. All right, then for the squeezing phase, we want to first reset cursor and I to 0. So cursor is equal to 0 and I is equal to 0. And we're going to do kind of something similar, where the cursor is now the cursor for the and we actually don't need I anymore. So this I can actually just be in the for loop. I was making a mistake there. So that I is the block counter can just be in the for loop. We don't need it as a function variable. So the cursor is equal to 0. This is going to be the cursor for the output message string. All right, and what I said before about the squeezing phases, we're essentially just going to be continuing to add into the output until we have enough. So while cursor is less than ret length, then we're just going to we're going to go through the block and output it into the message. So integer block cursor equal to 0. So we need, I'm going to comment this with block variables. So this is going to be the cursor in the block. And then we're going to do a similar iteration. So for integer y is equal to 0, y is less than 5, y plus plus. And then for integer x equal to 0, x is less than 5, x plus plus. So the same way that we read in plane by plane, we're going to output plane by plane as well. So we start by going across the x values and then we go up through the y values. Alright, and then what we're going to say is if block cursor is less than r and cursor plus block cursor is less than ret length, then we want to take from the state, so copy from state to the output. And we're going to say memcopy the dereference of out plus cursor plus block cursor. So essentially we're going to be dividing up the output into blocks of length r. So the same way how we kind of took in, so where we memcopied in plus cursor plus block cursor, we're now going to be outputting to that same method where we do out plus cursor plus block cursor. First the cursor to get to the block, and then the cursor within the block. And then the source will be a at x plus y. So this is still a pointer to memory because it's a at x, and then we're doing some pointer arithmetic to get to the y value in the x within this x. And then the number of bytes to copy is just a single unsigned long. So size of unsigned long. And then block cursor plus equals 8. And then otherwise we're just going to break. And then outside of the x loop, we're going to say if block cursor is greater than or equal to r, or cursor plus block cursor is greater than or equal to ret length, then we have either completed the block or the output. Either completed block or the output. And we're only going to be reading or outputting r block or r bits at a time, which is just once again the bit rate. So we're going to break out of that loop, and then after the while loop iteration, we're going to say cursor plus equals r, and then we're going to call the Keccak function, which is just going to be SHA3 Keccak f and it's just pass an a as the state. Alright, and then after everything, we're just going to return the ret length. Alright, so that's the high level Keccak stuff. So we have completed the framework for all of this. So we have done the padding, the pre-processing, and then we've also done the inner Keccak. Now all we have to do is just do each round of Keccak. Alright, so Keccak rounds, that's the function up here. Alright, so we're going to start by doing theta. So step theta. For step theta, we're gonna need 2 arrays of unsigned longs. So unsigned long C of length 5, and unsigned long D of length 5 as well. So these are essentially going to be 2 planes. So it's a 1D array of a long. So 2 1D arrays of long. All right, then we're going to calculate C. We're going to say for integer x is equal to 0. X is less than 5, x plus plus. If you want to go into the specific details, I'm pretty much just copying the code from the documentation or the pseudocode in C, in C version. But once again, this is going to be our summation step. So for C, this is just going to be the stuff to the, we're going to XOR, we're going to XOR in all the values from the current, oh, I forgot what this is called. If we're doing it, C at x is equal to 0. So in the first line of this loop, it needs to be C at x is equal to 0 to set it to, just to set it to a 0 value, so 0L actually. And then for integer y is equal to 0, y is less than 5, y plus plus. And we're just going to XOR it in. So C at x is XOR equals with A at x at y. So this is just going to be the XOR of each sheet. So that's what this is called, a sheet. And then to calculate D, we're going to first have to rotate stuff. So for integer x is equal to 0, x is less than 5, x plus plus. Then D at x is equal to, now we're going to have to XOR each value in C with the rotated version of the state. So C at, now in parentheses, x plus 4 modulo 5. So the x plus 4 is in parentheses, and then we take that value modulo 5. This is essentially x minus 1 modulo 5, but I couldn't, the x minus 1 modulo 5 was not giving me positive values, only it was also giving me negative values. So x plus 4 modulo 5 will give the same stuff. So we're going to take the value at C, at this index here, and we're going to XOR that with SHA3 rotate word. So we're going to rotate the word, and the word to rotate is C at x, and then in parentheses x plus 1 that modulo 5, and we're going to rotate that by 1 position towards z is equal to 0. And then we're going to put the result into A. So for, it's just going to be the full loop. For integer x is equal to 0, x is less than 5, x plus plus. For integer y is equal to 0, y is less than 5, y plus plus. A at x at y XORs equal with D at x. So the way this works is we're calculating sheets, or we are taking sheets, which is just C and D, and then we are XORing them with their neighbors, which is this right here. So you can see how each one of these 5 things is just one column in the sheet, which is essentially how, and if we do that along the whole lane, we're just going to get 5 lanes on top of each other. So that's why we just need a single array of 5 longs, which is just a sheet. Alright, so that's theta. Then for rho and pi, you can do rho and pi in the same calculation, which is pretty nice. We're going to need an auxiliary array, so unsigned long b at 5 at 5. So it's a 5 by, it's essentially a copy of the state, or not a copy, but an auxiliary array, and we're going to set it to 0. So mem set b 0 is the value, and then 5 times 5 times the size of an unsigned long. I did forget to do one major thing in this function, but I'm going to do all the steps and then I will tell you what I forgot to do. So we set the memory to 0, and then we are going to iterate through each entry. So for integer x equal to 0, x is less than 5, x plus plus, for y goes from 0 to 5. And what we're going to say is b at y. You can check for the documentation, it's just pretty much the exact same. So b at y at, then in parentheses, 2 times x plus 3 times y, this modulo 5. So y is going to be the x coordinate that we're putting it at, and then 2 times x plus 3 times y, that reduced, will be the x coordinate, or the y coordinate now. And this is going to be equal to SHA3 rotate word by of a x y, and we're going to rotate it by the rotation constant corresponding to this lane. So SHA3 rotation constants at x at y. So that's essentially the row step, and then for the pi step, we're just going to, or sorry, that's row and pi in the same one. Essentially, row was doing the rotations, and then pi is shuffling them around. But you can just do it in one step without using another auxiliary array. And then for chi, or chi, I think it is, we're just going to be XORing in the auxiliary array with some modifications. So do the same loop. I'm actually just going to copy this double loop over so I don't have to type it out again. And then in each iteration through y, we're going to say a at x at y is equal to b at x at y, XORed with. So we're taking the value in the auxiliary array and XORing it with. Then do this in parentheses. We'll open one set of parentheses, open another set of parentheses. In the second set of parentheses, we're going to take the complement of b at then x plus 1, that modulo 5, and y. So b at x plus 1 modulo 5, add y, and you have to take the complement of that in parentheses, and you close the first set of parentheses, bitwise, and this with b at x plus 2 modulo 5, and then y. So take a look at that for a quick second. Make sure you got that down. But also, this is directly translated from the document here. Where is it? Yeah, here it is. So AX, that, and then we XORed with, is this it? Yeah, it is. Okay. All right, so that's chi, and then now for iota, you're going to realize I forgot something. So we're going to have the same loop, no, it's not the same loop. We're just going to say a at 0 XORs equals with something. Now what do we want to do? It's going to be the round constant. SHA3 round constant at what? I forgot to do the main loop in this function. So in each Keccak function, we're going to need to do a loop. So it's going to be for integer I is equal to 0, I is less than SHA3 NR, the macro, I plus plus. And then you need to put all these steps into this loop here. And then now for step iota, it's going to be a at 0 XORs equals with SHA3 round constants at I. So we get the ith round constant and XOR it with a at 0. And this function doesn't need to return anything because it just operates on the array, which is just a pointer. Give me 2 seconds, and then we'll go ahead and test this out. All right, now let's go to main.c. And I have nothing to test with. Good stuff. Okay, we can just do Alright, so let's just make an unsigned character message. This is going to be equal to, what do we want? I'll just do A, B, C, D, E, F. And then if, we'll say integer length is equal to SHA3 hash, the input is going to be message, the length of that is going to be 6. The mode will say SHA3 512, and then the output is going to be a variable that we need to allocate, or not allocate, but just create. So we'll have an unsigned char pointer hash, which is equal to null. And then we pass in a reference to hash into the function. And then we will call print character array, which we had from before. This is just going to print out in hexadecimal. Print out the hash length is going to be len, and then false. Hold on. So let's run this, and we got an error. Good stuff. SHA3 hash gives an undefined. I need to add the SHA3.c to the build path. Okay. Yep. All right. So SHA3.c. Yeah. Make sure you add it to the build path whenever. What happened? Oh, I put SHA3.c in the wrong folder. Okay. Now it should be good. Alright, so this is our hash for the message A, B, C, D, E, F. Let me get this in what's up here? What's this doing? SHA3 512 of A, B, C, D, E, F. Nope. Alright, so I'll say hash size is that, word size is 64, SHA3, the message text is A, B, C, D, E, F, calculate. Hash output is this thing right here, and we got it. So that's that. And it's correct, just not capitalized, of course. So that's that. So yeah, that's SHA-3 hash, secure hash algorithm 3, and we have it programmed in 3 different security levels. You can add more if you want. I'm going to be looking into modifying the output or the padding scheme just to see if I can make it a little more efficient instead of going through word by word. See if I can do anything about that. But yeah, so that is that. In the next video, I'm going to try and do an extension of this where I can do HMAC or PBKDF, password based, yeah, PBKDF2. Those 2 algorithms employ SHA-3, or can employ SHA-3, but I'll see if I can write them where they use SHA-3. So yeah, I hope you guys enjoyed. I'm going to try and figure out my schedule, but it will definitely be more stable as school starts. So yeah, hope you guys enjoyed. Hope you maybe learned something. And I will see you guys next time. Have a good one.